two classical reasons why we need quantum mechanics. This is the examples I'm going to give you come from probably high school physics, certainly first years of undergraduate studies. So this is the famous Stern-Gerlach experiment. Now, there is a furnace here. You can see the furnace. In the furnace, there is some silver, and then the silver the silver atoms are ejected, and silver has an odd number of electrons, and so there is the nucleus, and the odd number of electrons. They form a dipole. And the classical prediction, if the silver atom goes through a inhomogeneous magnetic field, is to form as you see here, a line of atoms. And instead, the actual prediction, the actual result, is that the silver atoms are deposited on the screen in two spots. But is this meaningful in terms of quantum mechanics? Do we really need quantum mechanics for this? Okay, let's say we say no. Why we don't need that? There is something in the atoms, in the silver atoms, that is special. We don't know what it is. But the fact that you have just two possibilities is exactly the same situation we have when we're dealing with a point that is projected onto the x-axis. So the answer is plus or minus. There is no difference. So for this, we don't know what's in the silver atoms that makes us give this result, but it's similar to what I would expect classically in a different field. However, and this is a big however, now let's suppose we select one of the two beams, we rotate the equipment, and then we put another screen at the end. And then if the rotation is 90 degrees, what would we expect? Well, we have selected one of the two axes, okay? We rotate the equipment by 90 degrees, so we expect to be orthogonal. And so we expect to have only one signal, okay? And the average value of the signal should be 0. If the rotation is not by 90 degrees, then we expect something that is proportional to the angle, probably the cosine of the angle, but it's neither here nor there. And yet, and this is the thing that makes us think quite a bit, and yet, when we do the rotation, we again obtain the two spots. So there is something very special. The system cannot answer in any way but with two values. Okay, so this is important. Let me give you another example. We take this again is from high school physics probably. Let's take a filter, and then we have unpolarized light. The unpolarized light goes through a filter, and then we have an equipment, and we detect the light at the end. Now we put two filters. And they are one perpendicular to the other, and then the light does not go through. This is it's very. Do we need quantum mechanics to explain it? Well, it's like closing a faucet. Okay, so it's like water not going through it. We are doing something, and the water is not going through. However, again, let's suppose now we have one filter. And then the first filter stays the same. The last filter stays the same. They are 90 degrees with respect to one another. And in between, we put this a filter that is oriented 45 degrees. And so we're closing the faucet slowly. And then what happens is the fact that the light goes through. And this is what make people think that there is something special. Of course, now we're dealing with atoms and with light, and the phenomena that are under these two examples are quite important. They have to be described quantum mechanically. However, okay, so we for atoms and light or spectroscopy or photochemistry, we may need quantum chemistry, or sorry, quantum mechanics and then quantum chemistry. But what about the rest of chemistry? Do we really need it? Or perhaps we're looking at something and then we're pointing at the moon, as the say goes, we're pointing at the moon and we are only seeing the finger. So we want to try and understand what we really need to do some modeling in chemistry. So let me show a couple of examples from real life. Okay, so let's consider a biosystem. Now here you see a muscle, and then inside the muscles there are fibers, and then the fibers are actually driven by the axons. And then as you go from the macroscopic world of the muscle down to the fibers and down, further down to the molecular level, actually the protein level, then you are going through an enormous range of length scales. And some of them are macroscopic, and down, 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 you go to the nanoscale. So here the issue is, can we reasonably describe all these length scale in the proper way using the same kind of theory? Of course, this is not there is not only the length scale, there is also the time scale. And the time scale, again, when I move my arm, is a time scale of seconds. But then when the actual motion of the proteins is on the microsecond time scale. And if I think a bit more, then around the proteins, there are, for instance, there are lots of ions, or there are electrons that move around. And so the point here is that the range of timescales is also enormous. We go from the picosecond or sub-picosecond all the way to the second and hours timescale. We're really covering an enormous amount of ground. Let's change completely the picture. Let's go to something that is becoming quite popular in chemistry. This is a kind of transistor. It's different from the transistors that are in my computer or your computer. This is called an OECT. It's basically, it's a wet transistor. It's not as efficient as a silicon transistor, but then it's based on the same type of approach that silicon transistors are based, but we have a fluid layer, and then we have a semiconductor layer. We have resistance. We have exactly the same thing that are present in silicon. Again, these things cannot, despite what people say, cannot really work better than silicon. However, for a number of reasons, they are much better than silicon when it comes to sensing activities. So when it comes to sorry, the light goes this. I don't know how to restore the light. Okay. When it comes, so for sensors, they are much better than their silicon counterpart. I will discuss that maybe later. So, but the point is, again, the motion of the liquid is on a certain time scale. Let's say it's in the nanosecond. The motion of the carrier of that can be electrons or holes in the active layer is on the nanosecond or the picosecond, and the response of the transistor is on the second time scale. So again, we have something that covers many time scales, and so do the length scales. And I can model this thing in a variety of ways. This is just stolen from a web page. It's not really important. But I can discuss this transistor simply in terms of electrical engineering and be quite happy about it. But then perhaps this is not the as a chemist, what I would really like to do, because as a chemist, I would like to have a molecular understanding of the entire situation. Let me provide another example, and this is CO2 sequestration. So we all know global warming, greenhouse effect, CO2 problems, and so on and so forth. So people think maybe we can take the CO2 and put it under the ground. And in order to do this, you can see here, if we want to design the system somehow, well, we need to collect the CO2 somehow, and then we need to understand how, once we put the CO2 inside the ground, what are the interactions. And so here you can see that we have to model the CO2 that interacts with the salted water, with the brine, and the length scale goes from centimeters to meters, and then inside the system that will sequester CO2, we have to go to a length scales that goes down to the nanometer, and then farther down the interaction between CO2 and the real chemical nature, of course, will be in the nano domain. And so again, the question is, can we model all of the above in one way, or we have to worry and think a bit more more deeply about the modeling. So let me tell you what chemistry is all about. Okay, this comes from a lecture that I gave recently, and now the chemistry is about trying to figure out what are the rules of the game. Any science is about, well, we can discuss it later. It's, in my opinion, not only my opinion, of course, it's about the rules of the game and about a language, an interpretation, a representation of reality. But in chemistry, we distinguish about the environment, okay? So the overall picture. And then there are so many different types of environment in chemistry. We can be in a polar fluid, we can be in the solid state, we can be in the gas phase, and all of them are very different. And there are so many different kinds of chemical systems. Actually, these are some of the chemical systems one can think of. And at odds with what usually happens, it's not, if we have a soccer pitch, of course, usually we play with a soccer ball, but this is not necessarily the case in chemistry. We can mix them all together. And then there are so many different kinds of players. This is truly what happens. And what do we have in chemistry in reality? Okay, this is the macroscopic picture. But if we want to push a classical analogy, the intent of chemistry is similar to try to learn the rules of a football or rugby or basketball or water polo match from the trajectory of the ball. So we know where the ball is in principle. This is what we know, but we don't even know the shape of the ball quite often. And I would argue that if we do modeling, we cannot use only one kind of model. We have to try and understand what is the best modeling for the best purpose. Okay. Why is that? Why does that happen? Okay, somebody said it's a riddle wrapped in a mystery inside an enigma. He was not talking about chemistry, but I find this citation quite enlightening. The real reason of the complexity is that chemistry depends on lots and lots of different players, different interactions. Plus, we have temperature, solvent effects, external forces, and depending on how we look at it, we can have to understand the entropy, or we have to understand tunneling effects. So we have a continuous interplay between classical and quantum properties. This is the situations we're dealing with. And why do they arise? This again is I don't know if you can see it. It is stolen from a rather important book by a very good scientist that passed away a few years ago, Israelachvili. And he pointed out that the complexity arises because we have covalent or metallic bonds, and this is the matter that actually quite often is of interest for a chemist. And then we have classical interactions that can become quantum, like charge-charge interactions, charge-dipole, dipole-dipole, charge non-polar interactions. What is a non-polar interaction? It is something that we learn as students, and hardly ever we quantify. These are the so-called hydrophobic interactions, for instance. And then we have transient interactions, and of great importance for chemistry and for biosystems, of course, is the hydrogen bond, which is a mixture of many of these kind of interactions, and still is being studied. So the thing that I find important is the fact that we need to use multi-scale modeling. We need, it's a must. We cannot get out of it. And when each and every scale will have its own type of modeling, of course, it would be fantastic, just fantastic, if we could rely on quantum mechanics, on pure quantum mechanics. However, then we would again look at the finger rather than the moon. And here is an explicative type of picture or slide, just to help focus the ideas. When we start with quantum mechanics and its application, that is quantum chemistry, we are actually able to deal with systems that go up to the nanometer, and then that is 10 to the minus 9 meters, of course. And then the time scale is actually something that results in the femtosecond, 10 to the minus 15, or 10 to the minus 12 seconds. And then here, we can understand a lot of things in terms of the behavior of the electrons or the holes, and behaviors our understanding is at the molecular orbital level, or band structure level, if you are in the solid state continuum. Then, if we want to go on to a different level, we have to use molecular dynamics. And molecular dynamics is actually can leverage on quantum mechanics and quantum chemistry. We can do molecular dynamics. What's dynamics? Of course, we all know the word, but then in chemistry is just the ability or the possibility to integrate the equations of motion. That is, I have a certain position, my system, that is, all the atoms are in a certain positions, and I know where the positions are. I know their momenta somehow. I can generate them randomly following certain rules, or I know them for some reason. And then I can integrate the equation of motions, that is, go on to a different, to move the positions almost infinitesimally by a fraction of an angstrom. This can be done using quantum chemistry, or, and then I will discuss it briefly later, or using classical potentials, which generate molecular mechanics. What happens here? Well, implicitly, I reduce the level of complexity because I don't have electrons anymore, usually, and I can increase the size of the system or the time scale of the system. And I can approach, say, the microsecond or the micron in terms of dimensions. And then I can go to the mesoscale. And in the mesoscale, and there are several ways of doing this. In the mesoscale, I have to get rid of the notion of atoms. So I have what are called usually beads or fragments. And then again, and here there are lots of problems in going from one system to the other, one approach to the other. And this is something that I will mention, I will discuss. And in the mesoscale, we have the beads. And since I'm moving to the mesoscale, I have to worry about a different type of description. Well, on the one hand, I have to really worry about thermodynamics, start worrying about thermodynamics. And on the other hand, I also have to worry about fluidodynamics. Okay, so, and I have to make sure that I don't make any silly mistake in this region, which is no man's land. And then I can go to finite elements, that is the macroscale, that is the way engineers work when they design a bridge or they design a device. Okay, and again, I can make the system bigger and bigger. Now, what happens in terms of calculations, of real calculations? We know as chemists, we can pull down from the web many of these, of the programs, of the computer programs, as people would call them nowadays. My students call them apps. I don't like that. It's not, these are not apps at all. These are truly complicated computer programs that requires a lot of expertise to understand what you're doing and why you're doing that and what's the theory that is behind. Many of my students just want to run them and show how good they are at running them and solving technical problems. I think they should study a bit more what's behind the theory that is behind it. But the point is, the point is here. When I start from quantum chemical calculations, then the theory is so well established that I know exactly the kind of approximations I'm making. I know I can use very approximate theory, I can use less approximate theories, but I know exactly where I stand. And so I, in principle, know the kind of accuracy or inaccuracy I have. We can use what's called ab initio, we can use what's called tight binding, we can use density functional theory, we can use lots of different things, but I know exactly where I stand. Then when I move to the molecular mechanics, molecular dynamics approach, then things are not that clear. I mean, I don't have the electrons. I don't have quantum mechanics to teach me what are the approximations. I still have one thing that I'll mention later to drive me, and that is good enough. And so again, I can pull down from the web or buy or purchase some of these programs and be quite happy about that. And then in the mesoscale, where the coarse graining starts, how do I go from classical, from quantum to this domain? Okay, to this domain. Well, it's not that trivial. Why is it's not trivial? Because I have to, as I said, make sure that from a domain where I hardly ever have to worry about entropy or thermodynamics, I really have to include that in my way of thinking. And then I go to the continuum. What's the problem with the continuum? I mean, I often have this discussion with the engineers. We know the equations, we solve the equations. Of course, you know the equation, you solve the equations. But when you do that, and you don't rely on the previous levels of theory, you are deciding that your system behaves according to the equation you have selected. And if you decide that your system behaves according to that, 99% of the times you will be quite happy. But as a chemist, as a scientist, I would like to know to investigate that 1% where things don't work out, because that's where they really become interesting. Okay, and the other thing is, okay, you simulate your system with the continuum equations, say Navier-Stokes, Poisson-Boltzmann, whatever you use. You simulate your system. However, where do you get the parameters? Well, the parameters are the parameters that reproduce the experiment. Sure, but with 4 parameters, I can reproduce an elephant, as somebody said, and with the 5th one, I can make his tail wiggle. Okay, so again, would be much better if I were able to use to obtain the parameters, maybe not highly accurate, but to get the parameters from the previous levels of theory. Okay, so let's see what are a bit more in detail, what are the characteristic time motions, the characteristic times of the motions. So if I have 2 atoms that are connected by a chemical bond, then the stretching, the bond can elongate and shorten in time, and the bond stretching is typically in a fraction of a picosecond, say 0.01 picosecond. The amplitude is 1 angstrom, roughly, 10 to the minus 10 meters. The bending is a bit slower. And then as I increase the mass or I increase the size, for instance, I take a CH3 carbon with 3 hydrogen atoms, the time scale goes up to the picosecond. But if I have a protein or a polymer, then the motion of a part of the polymer or a part of the protein is on the nanosecond to the microsecond. The amplitude of the motion, intrinsic amplitude, I'm not talking about reactivity or anything. The intrinsic motion, the size is of several angstroms, half a nanometer. And then if I go to consider a fluid, then again, I have to increase the time scale and the length scale. So what do we do with molecular modeling? Well, we have to select a goal, and we want to be able to simulate, again, something that I always discuss with the people. The big simulator, in chemistry, there are big simulators. They have a big computer, a high performance computer, and then they simulate anything. So experimentally, you get the perhaps infamous 42, is the number, if you know the Hitchhiker's Guide to the Galaxy, they built this huge supercomputer, and then they asked the supercomputer the meaning of the universe, and the meaning of the universe is 42. Perhaps you've heard of it. And so they have to build another computer to ask another question, but it doesn't matter. But so you simulate the experimental result, but you already know the experimental result. Okay, so what's the point of it if you already know the experimental result? Well, if you simulate it, then you know that the theory that you use is the correct one. But I think what would be nice is to make prediction rather than simulating experimental results. And the predictions, of course, must be relevant to the macroscopic domain. And so we have to be able to understand the thermodynamic regime, predict the thermodynamic and the kinetic regime. That is, thermodynamics is the energy, of course, you know, the energy that includes the effects of temperature, so to speak, and the kinetic regime is where we are, it is the time dependence, okay. And not only we want to reproduce energies, but we would like to be able to predict diffusion, migration of particles folding, association, partitioning of molecules between phases, the behavior of membranes, and so on and so forth. But when we do that, we are fighting against something that is important. On the one hand, we're fighting against the number of degrees of freedom, 3 multiplied the number of atoms that we are dealing with. We're fighting against a very complicated Hamiltonian. We're fighting against free energy and ultimately against entropy. And so there is a tyranny here, and we need to verify, validate, and determine the accuracy of the calculations. And we need to have an understanding of the software. We cannot use it as a black box, although nowadays many people tend to do that. And there is the emergence of big data in simulations. And as the systems grows, then we have problems with the visualization and imaging. And of course, we need to make everything better and proper. So there is room, before I get to some examples, there is room for intervention. As I said, we need a lot more, but what is really needed is are people, faculty staff, or people in the industry that are able to understand the mathematics and the applied quantum chemistry that is at the basis of all the simulations. There is no, as far as I know, there is no real book that deals with all these time scales and length scale, perhaps because we need people like you who discuss them more properly and in a wider context. There are no best practices for multi-scale simulations. And then even more importantly, sometimes we don't even know how to validate the new approaches that we're dealing with. So multi-scale is a, here something happened, okay. Multi-scale modeling is a necessity, and it's a necessity because we want to go from the pure chemistry to the engineering and tell them what actually is the best model to deal with. And we need to understand, when we're dealing with computational chemistry, the interplay between experiments and first principles. So what I will be discussing, I've taken a longer time than I thought, what I will be discussing now are 3 major points. One is our ab initio models, and the meaning of ab initio models in quantum chemistry. The second point is molecular mechanics, molecular dynamics, and then the coarse-grained approaches. There are lots of other things I could be discussing with you, but for instance, one is the theory of signals that I think is becoming extremely important nowadays, but of course there will be no room for that. Okay, so what is ab initio? Ab initio is something that we all know from our high school studies, and actually in English it means something completely different. It's taken to mean from first principle. Okay, so first principles, and ideally it refers to the fact that no experimental data are used in these calculations. So on the one hand, this does not mean at all that the calculations are accurate, not at all. There's no, the calculations can be off the mark by a very long shot. However, there are no experimental data. Is it true? Sort of, not quite, okay. Perhaps the most famous ab initio calculation is the so-called Hartree-Fock approach, which has lots of shortcomings, and the disadvantage is that the the approximation is such that the electrons don't truly. Now, if somebody hears me saying this, I will be chased out of town. But the electrons, to a certain extent, don't truly interact with one another. Okay, so it's. But then, so the electron correlation is actually what is not taken into account. And then one can go on to develop a perturbative approach, which is called in chemistry Muller-Placet theory, or one can branch out to density functional theory. One can go on and do configuration interactions, couple clusters, lots of different things. So the point here is I write down a Hamiltonian, and of course the Hamiltonian is something that I can write quite simply, and then I try to solve it. What is quantum chemistry, this ab initio thing, good at? Well, it describes well the shapes of the molecules, reasonably well. That is, the bond length and the bond angles, and the electron density. It can be used to calculate reaction pathways, that is, reaction mechanism. We know usually we go to the wet lab, we put up a reaction, we know the reactants, we know the products, but what happens in between is something that has to be understood, because usually in chemistry, reactions don't go 100%. So there are also all sort of side products. We can determine reaction intermediates, transition states, and the approach is very good to understand what the molecular orbitals. Oops. Okay, so what is the problem here? Here you see an equation. Well, this is a typical Hamiltonian. Now, don't look at this thing. So here is the first term are the kinetic energies of here are only the electrons, but we will also have the kinetic energies of the nuclei. And then we have the electron potential energy term. This is in h bar units, so we don't have to worry about all sorts of different funny quantities that usually go there. And then we have the interactions between the nuclei and the electrons. So let's take water, okay? So which is probably a very simple system. So there are 3 nuclei, and then 2 electrons for the 2 hydrogen atoms, 8 electrons for the 8 electrons for the electrons for the oxygen atom. So it makes for 13 particles. So this Hamiltonian, just in terms of kinetic energy, is 39-dimensional, plus all the interactions the Coulomb interactions. And of course, we have to solve it quantum chemically. We have to solve it somehow, and this is not a trivial thing. For CO2, the example I gave before, the problem becomes we have 22 electrons. Let's forget about the nuclei, and then we have a 66-dimensional problem. This is a tall order to satisfy, okay? So it's not trivial. So, and here is the thing. If we want to solve that, approximations must be used. Now, this is not to say that we are using experimental data, but the approximations we use actually must be of some kind. And in a sense, they are not truly empirical, but in a sense, they are empirical, especially when we do density functional theory. So let's change the picture here. So here we have a very high dimensionality, but then comes in density functional theory. And what does density functional theory say? It says, let's forget about the entire thing. We have a density, an electron density, and the electron density depends on the 3 coordinates, the 3 Cartesian coordinates, x, y, and z. And if we can sort of focus just on the density, then rather than having this huge dimensionality of the problem, we just have 3 dimensions to worry about. And so if we focus on these 3 dimensions and we calculate the density, hopefully, the electron density, the charge density, hopefully we can solve everything properly. Is it true? Well, sometimes it's true, but in chemistry, this hardly ever occurs. DFT comes in a variety of flavors, and they are, of course, they have different levels of approximations, and some are good for one thing, some are good for another things, and then it can mix. The chemists have mixed it with the previous level of theory that I discussed, which of course gives up the possibility of using just something that is 3-dimensional, but it can give very good results. The reason is that if we want to calculate the density, then we have to introduce something special in here, which is the not only the Coulomb interactions, but it's the exchange interaction. And we do not have any idea of what is the exchange interactions between electrons, but we can guess it, okay? So again, it does not rely on experimental data, but actually it does rely on a degree of empirical approach. So this is this exchange potential is something that is related to the problem of introducing correlation, electron correlation. It would be a very interesting lecture in the future to talk about correlation, not only in chemistry, not only for the electrons, but what correlation actually amounts to in chemistry. Okay, so what's the real difficulty here? The difficulty is let's see. I don't know how to do it. It's my first day here, so the real problem is how you solve it practically, and to solve it practically in chemistry, usually, as in physics, we need a mathematical approach. We need a basis set, and the basis set in general that comes out from simple atoms is something where we have the basis sets that go down, that tends to 0, or have to go to 0 at infinite distance, and so they are expressed as exponentials. Notice that in this thing, n multiply the exponential of minus alpha r, we have only the distance contributions. There is no angular contributions, which actually has to be there. But then chemists usually don't like exponential basis set for a number of practical reasons, and so they use Gaussian. Again, we introduce this empirically, and then and the Gaussians are set up in such a way that we have to mimic the exponential, that is the Slater orbitals. If we want to increase the size of the systems we are dealing with, then we can go to semi-empirical methods. Semi-empirical methods are based on quantum methods, just as the methods that I've shortly discussed now. However, some of the quantities that are in there are parameterized on experimental results, and so this simplifies the approach very much, and this is the way to deal with that. Now, okay, before I move on to some examples, I would like to mention something that I find quite important. Do we need at this level to deal with this kind of approach, or can we do something entirely different? Well, here is an example of what people do. They rewrite the problem of the densities and the all problems in chemistry. This is an approach that is quite interesting. I'm not sure I'll be able to come through, but they say, look, I can write the energy of a system not in terms of a Hamiltonian, not at all, but I can do a power series expansion of the energy in terms of the charges of the atoms, the local charges. Okay, so that this is the difference between the charge of the electrons that are localized, sort of localized around an atom, and the nucleus. And then so this is the Q of I here. And then if I do this, if I do the power series, then I can use quantities that appear here in the power series expansion that basically are related to the ionization potential and the electron affinity. This is important. Why is important? I do a classical expansion, but what I plug into the classical expansion are quantities that are intrinsically quantum mechanical in nature. Okay, so this is what people, and this is the opens all sorts of different possibilities. However, again, there is a big however. The thing is, I can do this exactly for a single atom, and then when I make atoms interact with one another, then trouble starts, because I don't know any possible way to make this interaction in practical terms. And since I don't know any way, I have to guess it, exactly like I have to guess the exchange potential. And it can be shown that at the end of the day, I can rewrite molecules, I can describe molecules using electron affinity and ionization potentials, which are quantum mechanical quantities in terms of a minimal circuit element. And people have been doing this, and there are a number of applications that are coming around these days. Okay, so let me give you some examples from my background, 2 examples. Now, one is about quantum dynamics. Okay, I've not introduced quantum dynamics per se, but the point is quite important. If you go to the holy textbooks, they will give you the principles of or the postulates, or call them whatever you want, of quantum mechanics. And depending on the book you select, you get, well, the first postulate is the fact that the system is described by a wave function, the second. But in others, they just say, look, the time-dependent Schrödinger equation is all you need to do that. And if we have the time-dependent Schrödinger equation, why not to integrate it in time? Okay, so this is, and see what happens to the system. And so we cannot do it analytically, we cannot do it on the back of an envelope, but we can do it numerically. And so this is a way to do it, a way, so H here in bold is the Hamiltonian of the system, the psi of t is the initial wave function, and then we can integrate it in time. It's something that probably 20, 30 years ago would have been anathema. That is something that people would not do, but now has become quite popular and standard. And so here you see, I have the psi of t that is defined in space and at a certain time, and then I redefine at the next time t plus delta t the wave function. This is not a stationary state, is not an eigenfunction of the Hamiltonian, otherwise I would be able to do it analytically. And the problem I will discuss here is quite simple in principle, although many papers have appeared on the topic. You know DNA, you know that DNA can get damaged, and it can get damaged by light. And what happens is that 2 DNA bases thymine bases react with one another, and they form a four-membered ring. And of course, this is no good because it may lead to cancer. And so of course, nature is a step ahead, and it has developed a protein, an enzyme called photolyase, and photolyase goes to the lesion and uses light to repair the lesion and separate the two bases. And now the issue that we were discussing is, how does that happen in terms of electron rearrangement, and what is actually driving this thing? And so what we did initially was just to localize the electrons on the active sites, this FADH site of the protein, and then see how the electron would move to the lesion, the DNA, where the DNA has the problem. And by integrating the equation of motion, we were able to see that, of course, this is just driven by, in a sense, by energy differences. The electron moves over there, and what we found is this kind of oscillating behavior. This is not unexpected. Oops, this is not unexpected at all, because if the psi of t were a wave function, then of course the motion would be entirely periodic, but since it's not, then it has a periodic component and then a non-stationary component, and this is what happens. And one would have been quite happy with that, but of course we were not happy, because we looked at the molecular orbitals that were involved, that is the positions that were involved in the electron transfer. And we found that all sort of different molecular orbitals were involved. And this, in a sense, goes against what we would expect of nature. Nature is very precise. It's like a surgeon. It's very good at doing things in the proper way without wasting or with a minimal waste. And so we went back to consider our system. And then we said, look, what is really nature doing? How can nature operate not using the whole spectrum of energies, but just doing something special? So what we did here, you see this gamma psi of double I, we introduced something that is called a noise. And the noise basically changed slightly the energy of the orbitals that were involved originally. Why does that happen? Why it can happen in practice? Well, there can be a water molecule passing by. There can be a slight reorientation of a protein fragment. There can be lots of different reasons. So it simulates a bit better the environment. And as we did that, one can use this noise term as white noise. And if one does that, well, the situation does not truly improve. Well, we go from, we reduce the number of orbitals that are involved, but then we decided to change the type of noise that affected the position of the orbitals, the energy position of the orbitals. And when we did that, we decided to use something that looked like, not quite, but what we did, we kept constant the perturbation for a certain time. But if we keep constant the perturbation for a certain time, we are introducing a degree of correlation, that is, the energy stays the same for a certain time. And introducing this degree of correlation, basically, of course, we introduce correlated noise, and which is in between what is called pink noise and red noise. Red noise is Brownian motion, and pink noise is the perhaps is the noise that the brain follows in its functioning, or is the noise of classical music. Okay, so it's quite important noise. And if you do that, so introduce this noise that is in between pink and red noise, then the picture changes completely, and only very few orbitals contribute. And so this is probably what nature is doing to promote the healing of the lesion. Let me go to an entirely different type of problem. And this is related to the example that I discussed previously of the organic transistor, of the electrochemical transistor. And now, as I said, one can use this thing in different ways. And here is a classical polymer that is used to construct these devices. One is called P dot. I mean, probably you cannot see this, but this is an entirely pi conjugated system. Is like so there is double bond, single bond, double bond, single bond, double bonds, and single bond. And if one uses this is usually developed in a formulation with another polymer that is called PSS that has sulfonyl groups, and if one uses only one of the two of them, then the devices that one can build are not or fabricate are not good enough. The combinations of the two is quite good, so much so that actually this polymer, this P.PSS, is used industrially as an antistatic polymer. And one would like to know if one can use this entire setup to detect molecules. And since we are there, the idea would be to see if we change one of the two components, that is the PSS, the non-conductive part, using Nafion. Say Nafion is the thing that is used in the non-stick pans. How things would change. Okay, so we wanted to compare the two of them, and if one looks at the molecular orbitals or the energetics of the thing, one does not find much to say in the comparison of the two. One can calculate the binding energies, the interaction energies, all sorts of different things, but there isn't much there. And then one can use several levels of theory to analyze these things. And what eventually one can discover is why one of the two systems works to detect other molecules and why the other does not work properly. And at the end of the day, the reason is the position where the analyte, that is the thing that actually has to be detected, ends up, and how it affects the electron distribution of the polymer. So one can use these approaches to solve real problems. And of course, in the process of doing this, a variety of methods of quantum chemistry are used. Now, here there is a blank slide, and the reason is that I would like to switch to molecular mechanics. Now, there are several ways of looking at molecular mechanics. Molecular mechanics is basically a Newtonian approach to molecules. And one can say, look, I describe a bond as a classical harmonic oscillator, or I describe a torsional angle as something more complicated. But there is a foundation for this. And the foundation is spelled out here. It's the Born-Oppenheimer approximation. So what's the Born-Oppenheimer approximation? I did my PhD thesis on a great part of my PhD thesis on this, but the Born-Oppenheimer approximation in the popular press, when it pops up, that's not quite often, but also for many chemists, is the fact that you can separate the electronic motions from the nuclear motions. And the rationale that is given is that the masses of the nuclei are much heavier than the masses of the electrons. And so in practice, sorry, excuse me, what you see is that the nuclei effectively are frozen with respect to the motion of the electrons. And so you can calculate the energies of the distortion of, say, of a bond or an angle or whatever, just point by point. I don't think this is correct, but this is a never-ending war that I wage against these ideas. In quantum mechanics, we don't have, well, we have the masses, okay? Of course, we have the masses. However, in quantum mechanics, we talk about the energies, okay? The masses enter quantum mechanics, but the true thing is that what enters are the masses. Are the energies. And the energies, the electronic energies, are very different from the vibrational energies, and that's why we can separate them. Okay, this is the fundamental. But regardless of my of the thing that I just mentioned, there is a foundation, a theoretical foundation for molecular mechanics, and it's interesting historically to discuss the very first molecular. I'll stop when you tell me, okay? The very first molecular dynamics simulation. The very first was done by the group of Fermi, and it was never published. It was never published. It's in the unpublished paper in the Chicago Library or somewhere of Fermi. And these are the people who contributed to the work. And what they wanted to show was to set up a string, not really with lots of different points, connected by a harmonic, a classical harmonic oscillator, and then they gave it energy. At the time, no temperature was possible. There was the system was not adiabatically connected to a bath, but what they wanted to show basically was the existence of the validity, the validity of the equipartition energy of the equipartition theorem. That is, they wanted to connect to the ergodic hypothesis. And this is not what they observed, not at all. That's why Fermi never published this work. What they observed was that the energy would go back and forth along the string of points connected by harmonic oscillators. They would go just back and forth. So they thought that it was some kind of numerical artifact. But actually what they had discovered was the existence of solitons. And this would be quite interesting. So the point is that they solved it on the very first computer, and then they found something that they could not explain. And despite the fact that Fermi was a genius and had a very fundamental understanding of nature, in this case, he sort of did not was unable to rely to something fundamental like soliton theory. Now, what are the objectives of molecular dynamics? Well, the objectives of molecular dynamics is to approach the thermodynamic conditions, to introduce new degrees of freedom, typically solvent environment, and to vary greatly the composition. So to make the thing more and more complicated. And the applications are enormous. So we can investigate liquid solution, electrolytes, polymers, all sorts of different polymers, of course, carbohydrates, polymers, proteins, DNA, RNA, membranes, crystals, glasses, zeolites, metals. And we can all sorts of different processes, melting, adsorption, segregation, formation of complexes, folding of proteins and polymers. Well, you can read, I'm sure. So I will not spend more time. But we can do, using this kind of simulations, we can do lots of different things. What is molecular dynamics really about? It's about springs. Springs. We put springs between atoms, and the springs have to be carefully calibrated in order to obtain something that is trustworthy and meaningful. Look, there is an extra problem, and not only the calibration, that is the parameters that go into this thing, is also how we describe the systems. If we are close to equilibrium, then a covalent bond can be described by a parabola here. But if we go farther away, of course, we know that bonds dissociate, and so we have to change the equation that describes this thing. And then what is ultimately very difficult to describe are the so-called non-bonding interactions. The most famous of the non-bonding interactions, of course, is the hydrogen bonds, but then hydrophobic and hydrophilic interactions and van der Waals interactions are, of course, extremely important to obtain proper things properly. Each atom is now simulated by a hard spherical particle. Remember this word, because if I have time, there will be soft particles that will come along. Each particle has a radius, and most importantly, each particle has a net charge, can have a net charge. This is devising the problem, the parameters that describe all these things is quite important. Usually, the forces are taken to be linear. That's why we use many people start describing molecular mechanics and molecular dynamics in terms of classical harmonic oscillators, because the force, the conservative force in that case, of course, is linear, which is good because we know how to deal with linear forces. But we have to put the degrees of freedom, the forces, the generation of the moments, of the velocities and the boundary conditions, all sorts of different things in the same model. Here I'll show you what is typically a force, what typically a force field looks like. This is not a quantum force field, it's a classical force field. The Born-Oppenheimer approximation is under this approach. And here you see the bonds. For instance, we have a sum over all the bonds, 1/2 kb. Kb is the force constant. B minus B naught square. This is a classical harmonic oscillator. Same thing for the angles. Same thing for improper dihedral, that is parameterization angles. And then we have other terms that actually depends on the torsional coordinates, so they have an angular dependence. The first three terms are harmonic, and then we go into the non-harmonic terms like torsional potentials, and this r to the -12 and r to the -6 terms are typically Lennard-Jones, and then we have the Coulomb interactions here, where the Q of i's and Q of j's are local charges, which can be fractional. Okay, lots of different things can be done to deal with these things. The cross terms are the critical terms, are the very important ones, and we have lots of different approaches to do this, more or less. Okay, so we have approaches that describe proteins, approaches that describe organic molecules, approaches that describe materials, and each one of them covers, while ab initio or quantum chemistry covers the whole of chemistry. Here we have a blanket, and the blanket has, of course, its own size, and we cannot describe everything in the proper way. We gain in the size of the system and the time of the time length of the simulations, but we lose something in the complexity of the system that we can describe. Here. What can we describe? Where we take the parameters, sorry. We take them from experimental data as much as we can. We use crystal structures, we use heat of vaporization densities in the condensed phase, partition coefficient, diffusion coefficient, enthalpy, free energy, and so on and so forth. We also use data from quantum mechanics or in quantum chemical calculations. There is a crucial thing, really crucial, the really fundamental thing that is important, and these are the local charges that I mentioned before. And the local charges are crucial because when we have non-bonding interactions, of course, the positive charge will have to go to the negative charge. But if the balance between the two of them, then we will have the collapse of the system, and the charges will take over the simulation, and the other forces will become less and less important. So there are all sorts of different ways to calculate these charges. I will not dwell upon them, and as I said, they have to be carefully balanced. Now, oops. What's the problem? Now, something that does not come up with with quantum chemistry, and the problem is how we deal with the global potential energy surface. This is a typical example. Let's suppose we have a very narrow well here and a very broad well here. The narrow well is very deep, and the broad well is quite shallow. Now, where do you think the system will go if it explores them all? It depends on the area, on the number of states that are here and the number of states that are there. So all sorts of artifacts can come up. And also the system can switch between different states. And so the way we do the averaging is quite important. And the averaging, usually we do in the most trivial way, but then we know that the probability distribution function can be quite different. And so it can be quite tricky to do the averaging. This is how we integrate the equation of motion. What molecular dynamics allow to do nowadays, they have been able to do it for the last 40 or 50 years or so, is to introduce temperature, which is something that cannot be done usually in quantum chemical calculations. And one can introduce temperature and freeze it somehow and keep it constant. And of course, the problem applies also to volume and pressure, that they have to be dealt with in the proper way. There are all sorts of different ways to do it, also including ab initio. But then let me, since in principle I have only 10 minutes, I guess, let me give you a typical example of what we can do. I'll give you just an example because it took longer than I thought. Let's take lots of different proteins, okay? There are, in the Brookhaven database, there are more than 200,000 structures of proteins. And let's take lots of nanoparticles, okay? The chemists have been able, material scientists have been able to create zillions of nanoparticles. They can go from fullerenes to gold nanoclusters to molybdenum disulfides to all sorts of different things. So if we want to know, we can use these methods to know which nanoparticle interacts the most with which proteins, okay? So this is the typical thing that one can do. And then we can rank them. And this bears, of course, on the toxicity of nanoparticles and also on the possibility of using nanoparticles as drugs. One can then validate the results using experimental data. Let me and then the results, once validated experimentally, are usually quite good. So let me spend very few minutes on the coarse graining procedures. Okay, so the first coarse graining that chemists ever did was to use a united atom approach. What's the united atom approach? CH2 is a methylene fragment, CH3 is a methyl fragment. So what they did was to take all the hydrogens and put them to reside, so to speak, on the heavy atom, so that a fragment would be represented by a hard particle. So a CH2 would be represented by, or a CH3 by only one particle. What's the real danger when we do that? I mean, we have a CH2, and the CH2 or CH3 or no H or whatever, an H2, and then why shouldn't, for sake of getting a faster result, why should we not put it in to make it ineffective? We increase the size of the heavy atom. So what's really the danger here? Well, the danger is the fact that now these atoms would move on their own right. For instance, a methyl group would spin around. And so if we do this trick, then we lose the degrees of freedom that can be thermally populated. And if they can be thermally populated, then they contribute to entropy. So we're losing entropy when we do that. So we have to be quite careful about what we do, because otherwise, if we want to represent the system properly, we need to have a proper description of the free energy and of course the free energy depends on the entropy. So the method I advocate is using dissipative particle dynamics. What is, just to give you the flavor of this thing, what is dissipative particle dynamics? Well, it basically is a generalization of the Florey-Huggins theory that perhaps you have heard about. Florey got a Nobel Prize for this theory. And basically, rather than having hard particles, we have soft particles. So the soft particles represent a part of the system. It's like taking the hydrogen atoms and putting them in the heavy atom. But the particle is soft, so they can interpenetrate with one another. And if they interpenetrate one another, then they behave like a particle of fluid. And so we don't lose the entropy. We can still have the proper entropy. And we can do very big simulations. We lose the atomistic level of theory. And what we do, we describe the system in terms of three forces. Before we describe the system in terms of energy, now we describe the system in terms of classical, or truly classical dynamics, that is in terms of forces. We have a conservative force, and the conservative force is linear and actually is truncated, so is even simpler than the harmonic approximation. And then we have dissipative and random forces, and by fluctuation dissipation theory, the two of them at equilibrium are related. The point is this: we have dissipative forces, random forces, and conservative forces. They enforce a thermostat. We can also enforce it from the outside by enforce a thermostat, and the particles can interpenetrate. And by this, we can do lots of different things. We can describe big nanoparticles, but we can describe even living cells. I had prepared something on how and why one can parameterize this thing, but this was a big problem given up to us by some experimentalists. They, depending on the month of the year they did the experiment, they got different results with the same system. So they came to me and said, why do we get different results? I said, if you want me to include in a simulation the month of the year, I will not be able to do it, but I can change ever so slightly the parameters. And if I change them, I can go from this layered system to this complicated entangled system to this super micelle system. And then indeed, by changing slightly the interactions, one can obtain all of them. So the reason why I think we discussed it at length, we have not published yet this result, but the reason why they get in July, October, and November different results is because the amount of humidity in the air is different, okay? And that we are able to simulate, and also the external heat. If one does that, we can address a variety of problems. Here, for instance, is the best way to simulate the effect of a catalyst that is embedded inside an aggregation of molecules and see what is the best way to do it. In retrospect, I can tell you immediately what's the best way. If we bring the catalyst into an environment where, inverted commas, does not want to stay, and so I have to solvate it, then the best way to get the best effect of the catalyst is to have a dynamic system where sometimes the catalyst attempts to go out of the solvation shell. Lots of different things. But with this approach, we were even able to simulate living cells. Here you see what living cells do when they are put on different patterns. The patterns here is a hexagonal pattern. You see here is a pentagonal pattern. Here is a quadrilateral pattern, and so on and so forth. And we simulated the interaction with of the living cells, where the beads were actually done according to the theory that I attempted to outline before, and we can reproduce the pattern and then understand what happens. So we have gone through a number of approaches. There are many more approaches that we could discuss. Also, as I said, would be nice to discuss signal processing, not the way the engineers do it, but the way I see it. And I would like to close with a citation from a theoretical chemist that I like very much. And the citation is this: anyone can do calculations nowadays, but anyone can also operate a scalpel. That does not mean at all that all our medical and surgical problems are solved. And with this, I'm finished.